Hello, and welcome back to the course on distributed systems and security. This will be the first video out of a total of 5 talking about synchronous agreement. When I left you last time, at least if you are seeing this video in the order they were recorded, you were left with a cliffhanger of how to do what we call Byzantine broadcast with 4 corruptions, out of which 2 could be Byzantine corrupted. That means like 2 out of 4 servers in the network was trying to make the other servers confused about which message was sent by in this case, corrupted sender. You will learn how to do that by video 2. But first I will do a video where I'm in a bit more systematic way setting the stages for this synchronous agreement. And then also showing you an impossibility result. So in this video, we will see that if you want to be able to tolerate 1/3 corruptions, for example, having 3 servers out of which 1 is corrupted, we actually have to use signatures. So there's no way around using, for example, only authenticated channels. Rather, I'll show you we cannot do it with only authenticated channels. And then by video 2, I'll show you how to do it with signatures, including solving for you the cliffhanger. Okay, so video 1 will set the stage, talk about impossibility with authenticated channels, at least if you have many corruptions. By video 2, we will then look at how to do broadcast using signatures using a protocol called Strong. And that is for any number of corruptions. So even if you have 98 out of 100 servers corrupted, we can do it. Then we'll return to the case with only authenticated channels and talk a bit about why that is interesting, and show that you can in fact do it as long as you have sharply less than 1/3 corruptions. For example, 1 out of 4. That's a nice protocol for that we'll look into. Then we'll look at a protocol that's very related to broadcast called Byzantine agreement. It's the voting equivalent of it. And then at the very end, dive into something rather theoretical, which is namely showing that if you want to solve these problems, Byzantine broadcast or Byzantine agreement, in fact, you need to use a lot of rounds of communication. And we'll see that, for example, the Strong protocol uses a lot of rounds of communication. And what we'll actually do in the end is proving we're not stupid. They have to. We can actually prove that that is necessary. So that's the menu, but let's start by setting the stage. Setting the stage, impossibility of Byzantine broadcast for 1/3 corruption using only authenticated channels. So what do we mean by broadcast? In this case, it's essential to emphasize Byzantine broadcast. So what we mean is that some sender, will typically say player 1, wants to send a message to all the other players. And we want that all the other players always agree what was the message sent, okay? So of course, if we had like a whiteboard or a billboard, that would be easy. The sender would write it on the billboard and everyone could see the same message. But in a world where we just have IP connection between the machines, a corrupted sender could send one message to one party and another message to another party. And if what we are trying to do is, for example, a state machine replication, where we are running the same service on different machines, this could be dangerous because maybe now they disagree what was the input to the service. On one machine, one of Amazon's replicas, I bought, I don't know, a rowing boat, and on the other one, I bought a book. And therefore, I mean, my accounts will look different. I mean, that would be rather dangerous for a service like that one. So that's one example why we would like to do broadcast. And in fact, it turns out that if we can do broadcast securely against Byzantine corruptions, there's a lot of other seemingly very hard problems like state machine replication that suddenly becomes very easy. So it's a very nice problem to solve. So let's try to formalize it a bit more. So we have n parties, P1 up to Pn. We have some sender PI. In fact, I will make it P1 for the rest of the talk probably. Let's say anyone can be a sender for now. PI gets as input a message MI. That's the message that PI is instructed to broadcast by its API or its user layer. And then each PGA, each of the other machines will eventually output some message, let's call it MJ. This is what they deliver on their API. That's what they tell their application layer. This is the message that was broadcast by the sender. Then we require 3 properties, a liveness one and 2 safety ones. So the liveness one says, I mean, the protocol should terminate. It should at some point deliver outputs. And it's actually a little bit of a safety condition in there also, which says that these outputs should actually be delivered in the same round. I'll return to that in a second why we have to say that. I actually know let's cover that here. The reason why we want to do this is composition of protocols. So if we have a protocol where I broadcast a message and then maybe after 7 rounds it delivers at some of you, and some other parties it only delivers at round 8. And if we have a protocol of the type, first Jesper broadcasts a message, then Daniel does it, then Peter does it. Then in the second round where Daniel is to broadcast a message, that would start in different rounds at different servers. So some parties thought that I had my message delivered in round 7, others thought that it was in round 8. So they start running the next broadcast protocol in different rounds. And as we have discussed in round-based protocols, it's important that all parties start the protocols in the same round at the same time. So it's really just to assure that waiting for protocol to terminate and then continuing do not desynchronize it. It's quite important that synchronous protocols deliver outputs in the same round. That's just a tiny subtlety. Let's not think much more about that. And then the 2 important properties, which are called validity and agreement. Okay, so first, validity says the output should not be silly. I mean, it should be the right output. So if the sender is honest, then the message that everyone receives is what the sender intended to send. That's a reasonable condition, right? And then there's agreement, which says, and even if some of the players are corrupted, maybe even the sender, it should not be possible to confuse the honest parties. So it says, if honest parties PJ and PK output respectively MJ and MK, then these messages are equal. Okay? So that's the definition. How hard can that be? Turns out that can be quite hard because we're talking about Byzantine errors here, people that's trying to confuse the others. This is what I already presented on the previous slide. This is the slide saying, it's important to terminate in the same round, otherwise you don't start the next broadcast in the same round, then you will desynchronize, and that is bad for round-based protocols. So now let's try to dive into this agreement problem here and kind of start opening up our minds and learning first to be worried about agreement problems because they're extremely subtle and extremely hard to solve. And then even becoming so good to think about them that we can actually solve them. And it's worth actually spending some time both proving how we can solve these problems and in which cases we can't, because it will teach you to think about other problems in other settings later. So you're not trying to solve something that's impossible, because that's silly, okay? And that takes a little bit of time to get used to realizing when these problems are impossible to solve. And unfortunately, in distributed protocols, problems easily get impossible to solve because servers are separated from each other in time and in distance. And sometimes they can't maybe even talk to each other, and then things very easily becomes impossible. Okay, well, let's start with the broadcast case. Before I dive into that, just one warning and one more like a comfort maybe. In the book, we formalized broadcast also using one of these ideal functionalities. Remember that we like to formalize what a protocol is supposed to do by giving an ideal functionality. Now I just kind of, gave the trace properties, validity and agreement. In the book, just for completeness, we actually write this down as an ideal functionality. it's one of these cases where, in fact, the ideal functionality makes the world look very complicated, but it's not, right? It's really just, we're just writing down an ideal functionality here which have validity and agreement, and which terminates in the same round. And then you have to go through all these annoying details, like you have to say, you have to let the adversary tell when a message is delivered. And when it does that, I mean, that's on these delivery ports, it must also deliver to all the other ones. And this, of course, is because actually the parties using this box here violated the condition that they should also start the protocol in the same round. So you get all these annoying details you have to formally cover, which are important if you want to use this as a sub-protocol in something bigger, but it's really not important for our understanding. I propose that you read this ideal functionality here once, and then you don't have to beat yourself into having to remember this one and can replicate it at the exam. We won't require that from you. But if you're into modeling, try to read it and see how do we handle these formal details of formalizing such a thing as an ideal functionality. For now, we just stay at the level of agreement and validity. So what I will do now in the rest of this video is try to dive a little bit into the following case. Let's say we have 3 parties and one of them can be corrupted. We often call that the case n equals 3, t equals 1. We use t for historic reasons to denote the number of Byzantine corruptions. So I'm just going to say we have a sender and then I have 2 receivers, P1, P2, P3. I just rename them slightly here. So the sender is sending a message. And what does broadcast then really just require? It just requires that the 2 receivers will output the same message. And if the sender is honest and one of the receivers is honest, the receiver should output the message that the sender is intending to send. So that's the broadcast case in kind of the simplest possible, meaningfully possible setting. Now let's try to solve this problem here using only authenticated channels. So I'll just assume that parties can send messages to each other and they can trust that it was sent by the party that the message claims to come from. We could do that, for example, just by having each channel being authenticated using a message authentication code. We had a video on what that is. So the 2 endpoints share a secret key, and then they will just put a MAC on the messages so they can trust these messages as they're being exchanged. And then let's try to solve the simplest broadcast case, having 2 receivers agree on what the sender is sending. Okay? Can we do that? Let's try some protocols. Here's maybe the most naive one, which would just be, okay, let's try the following protocol. The sender will send the message to each of the 2 receivers, and then they will just output what they received. Okay, that seems trusting. But let's try just to exercise a little bit our definition here to see what properties does this protocol have. Does it have validity? It does have validity, because validity says that if the sender is honest, then all the honest receivers should output the intended message. They do, because that's kind of the entire protocol, that they will just trust what the sender sends and then output that. What about termination? Well, both of them output something and they do that in the same round, so there's also termination. What about agreement? What was agreement? Agreement said that the 2 receivers, if both of them are honest, then they should always output the same thing, okay? And this should hold even if there are corruptions. In this case, for example, the sender. And we see that agreement is obviously violated here because the sender could send 42 to receiver 1, 43 to receiver 2, and they were both trustingly outputted. And now they're inconsistent, and the rest of the application using these outputs is going to blow up and hurt everybody. So that was a bad protocol. We need to do more. We need to prevent that the sender can confuse us like this. Okay, then let's compare what he's sending. So here is protocol 2. The sender sends M to each receiver. They compare M1 and M2. I'm just going to call M1 the message received by receiver 1 and M2 the message received by receiver 2. So they have a nice authenticated channel here, so they can just exchange what they saw, and then let's try to make a decision based on that. Let's say if these two messages differ, so the sender is trying to confuse them, obviously, they will output no message. There's still a message, it's just they agree that the sender is corrupted, so we substitute it with no message. If the two messages, when they exchange what they saw, if that matched, then they will output that. Okay? So is that a good protocol? Well, it's easy to see now that it has termination and agreement. It has agreement because if R1 and R2 are honest, then they should output the same, but they do because they take what they see and then they exchange it. And then based on that view, which is the same at the two parties now, they make a decision. So they will always output the same. Yeah? The problem is now validity, because we could have a case where the sender is honest and R1 is honest, in which case R1 should send output what the sender is sending to R1. However, it could be that R2 is corrupted and forwards something else. So the sender is being honest and sending 42 and 42. And then R2 here claims, I received 43. So R1 would get 42 here, 43 here. So we'll go up and output no message. That is also cheating. But anyway, the protocol doesn't work. We can't just trust R2 here. Okay, let's try another one. So here's a third protocol, and I'm covering this one just to show that it's possible to get any two out of these three properties, but not all three at the same time. Okay, so we could have a protocol like this. The sender sends M to the two receivers. They compare them, they swap them again. Now, if they disagree, they will just do nothing. So they run forever. They just never return. They just start an infinite loop and doesn't output anything. Because we saw it was dangerous to output something. You could disagree, right? So let's just violate liveness instead. If they do agree, if the messages do agree, then they output the message, the matching message. So this one has agreement, because agreement says that if two honest parties output something, it should be the same. So one of them, we're just hacking the definition, say, so we don't output something, and we don't violate agreement. It's okay. We also have validity, because a party will only output a message if they match, and one of them came from the intended sender. So it only outputs something if it's actually the intended message. So it has both of these nice safety properties there, but now we did that by just killing liveness and saying, if we don't know what to do, we just do nothing. So that's kind of the three possible protocols in this code. And in fact, it turns out it's not because I'm stupid that I could not come up with a protocol that works. I put myself here, trying to look not stupid. It's in fact impossible to solve Byzantine broadcast in this setting here. I'm going to show you, because it's a cute proof, and I hope it can also help open your minds to thinking about distributed systems, trying to prove impossibility of settings, which should help you later in life if you're trying to solve a problem. It keeps beating back at you. Maybe it's because it's not possible. And these so-called scenario proofs here is a very strong way to try to prove impossibility of things. So here's what I would like to prove. I would like to prove that broadcast is impossible with n equal 3 servers and t equal 1 Byzantine corruptions and only authenticated channels. And the proof goes as follows. It's an impossibility. It's a proof by contradiction. So I'm going to assume that a protocol exists which have all three properties: agreement, validity, and termination. And then I'm going to prove that reach a contradiction. And then we have shown that so it doesn't exist. Okay. So here is the protocol I assume exists. I assume there is a protocol with three parties: P1, P2, P3, that solves Byzantine broadcast. Let me assume it for the simplest case, namely that P1 is just broadcasting a single bit. I'm going to to make P1 the broadcaster here. And it's just going to send a single bit to P2 and P3, and they should agree on what the bit is. Okay? Then I can do the really naughty thing here. I'm going to make 2 copies of P1. So, I mean, let's start up here, actually. Okay? So let's think of P1 for now being corrupted. And then P1 will run the following naughty strategy. So now inside this box here is the corrupted sender, the corrupted P1. It makes a copy of itself here and runs it with input 0. So it just takes its code for the protocol and input 0 to it. At the same time, it makes another copy of itself, sending 1. And then it connects the channels as follows. So see, P1 is over here and is connected to P2 with a dashed line, and is connected to P3 using a dotted line. We do that to be able to kind of map the channels to the other figures. So what I can do is I can take this copy here of P1 that is broadcasting as 0 and connect it correctly to P2. So put in another way, the corrupted P1 here is making a copy of itself and honestly talking to P2 using that copy. However, as for P3, we will make another copy of P1 broadcasting a 1, and that one talk to P3. And then I do this very weird thing here, that I take in this copy up here of P1, I take the channel that should be talking to P3, and whenever something is sent on that, I instead send it to the other copy of P1 inside the head of P1, and vice versa. If this copy here of P1, which is broadcasting a 1, sends something, there's a P1 here, that was intended for P2 here, I'll pass that to the other copy, okay? So you can see it as, in both cases, I have a P1 which have a dotted line, a dashed line and a dotted line, a dashed line and a dotted line. And for this one, I just connected the dashed line correctly. Here I connected the dotted line correctly. And then for the 2 copies, I took the dotted line and connected to the dashed line. So it just means whenever something is sent on that, I just move it to the other channel and input it to the other copy of P1. Right? It's clear this protocol should not do something reasonable, right? Because we have a copy of P1 up here. It's supposed to talk to a P3 on this channel, yet I connect it to like a copy of itself. So, I mean, if this protocol was programmed for setting like this protocol with 4 parties now, it should do something weird probably, right? But in fact, I will prove that it doesn't, and that will be our contradiction. I'll prove that it does several meaningful things, and these things contradict each other, okay? So the first thing we can prove is that if I run it in this configuration here, and I consider these 2 parties connected as a corrupted P1. Remember, we have Byzantine agreements, so a corrupted party is allowed to do whatever it wants. And P1 in particular would be allowed to deviate like this here, run crazy stuff in its head and exchange the messages as it wants. But notice we still have an honest party here and an honest party here. And then one corrupted P1 here doing something crazy. So I have 3 parties out of which only one is Byzantine corrupted. So the protocol should still do something reasonable. I mean, we should be able to tolerate that. And in particular, when the sender is corrupted and the 2 receivers are honest, we should have agreement so they will output the same. Okay? So no matter what P2 outputs up here, P3 will output the same. And it will output something because I assume all 3 properties, right? So by termination, they will both output something, and by agreement, it will be the same thing. So I need both of these properties. Okay? So that's already weird, right? I take a 3-party protocol like this, I make 2 copies of P1, I wire it all up weirdly, and yet P2 and P3 still output the same thing. But they must, because this is a legal strategy for Byzantine corrupted P1, and we assume we could tolerate that. Okay. Maybe some of you already guessed the proof by now. Because what I could do instead is I could take this, it's really a 4-party protocol now, wired oddly, right? And then I could instead consider these two here as one party, running inside, I just package them into one program that run the two other one as a subroutine. And then it will talk to P1 and P3. So since it's doing something weird and it's talking to a P1 and a P3, it should be considered a corrupted P2. So in the place of P2 up here, I could place this box, right? Notice that it would actually have the correct wiring. So if P2 is corrupted, we have P1 and P3 connected, and P1 has a dashed line to P2, and P3 has a full line. The same here, and then the weirdness only goes on inside this box. So I could really take a corrupted P2 and make it simulate this strategy here. What would happen in this case? Well, we have three parties. One is corrupted, so something good should happen because we can tolerate one Byzantine corruption. The sender is honest. We have an honest copy of P1 here. We have an honest receiver here. So by termination and validity, P3 will output something, and it will output the intended message broadcast by the honest sender. So in this case, P3 will output 1. Right? Let that sink in for a second, right? It must output a 1 here, because all this weirdness up here can really just be kept as a corrupted P2. So by validity, this weird stuff here is not allowed to confuse P3 into not outputting what this honest sender over here is outputting. And remember that P11 here, it was really just an honest copy of P1 running with input 1. Well, then let's look at this case over here. It's just a dual case, right? Now I have an honest P1, an honest P2, and then something that can be cast as a corrupted P3 in this figure up here. So that corresponds to one corrupted guy out of 3, and it corresponds to an honest sender with input 0 and an honest receiver. So by termination and validity, P3 will have to output 0, because this copy here of P1 is trying to broadcast a 0. I have now shown 3 properties of my 4-party protocol. I have proved that P3 outputs 1 always. I have proved that P2 always outputs 0. And I have proven that P2 and P3 always output the same. No. Right? These 3 properties are in contradiction. And therefore, this protocol here, which was my only premise, must be false. So there is no protocol for 3 parties that solves Byzantine broadcast with 1 corruption. So we were not stupid. And in fact, this proof here generalizes. It also tells us that you cannot do it with 30 servers, out of which 10 can be corrupted. Why? I'll give you 1 second to think about that. I'll give you time enough to press pause. So it's not just 1 out of 3, it's also 100 out of 300 and so on that we cannot tolerate. Okay? Some of the others might have pushed pause now, but you are still with me, so let me tell you. The reason is the following. Let's say I have a protocol with 300 servers, out of which I can tolerate that 100 is corrupted, and it's solving Byzantine broadcast. I can just take 100 of them and make them P1. So I just make a program which is running 100 copies of the small ones. It's running party 1 up to party 100. Party 2 in my 3-party protocol, I will have it run party 101 up to party 200. And party 3 will run party 201 up to party 300. Okay? And then when I want to broadcast something, I just have party 1 in the original protocol, the one with 300 parties, broadcast. And then we're just emulating. We're running all 300 parties, except 100 is being run inside this one, 100 inside here, and 100 inside. And then these P2 and P3, they'll just wait for one of the servers inside their copy, one of the honest ones, one of the servers to output something, and they'll take that as their output. And this, of course, works now, because if we take any setting where we corrupt one of the big parties, one of the ones that's emulating 100 of the other ones, that corresponds to corrupting 100 servers in the big protocol, right? Because each of these are running only 100 copies, small copies. So corrupting any of these corresponds to corrupting 100 in the original protocol, which the protocol could tolerate. So all the other servers will still have the needed security properties, including agreement and validity, and that clearly reflects then up to give validity and agreement in the emulated protocol. So it's really the three-party case that's the hard one, and impossibility of that reflects on all the other settings. So we can never, for any number of servers, if we only use authenticated channels, tolerate that 1/3 of the servers are corrupted. That's a bit disappointing. It means, like, for example, in this very juicy case of 3 servers, of which one could crash, which we considered for the file case, we see against the Byzantine fault, we actually cannot get agreement. That's a bit disappointing. Okay. That's the conclusion. Authenticated channels is not enough. Fortunately, and that's the next video, we can do it if we use signatures. So this is a case of this property that you also discussed when you looked at authenticity, that digital signatures are more powerful than message authentication codes, for example, in that they allow transferability. So what we're going to take away when we use digital signatures is the possibility of, for example, receiver 1 to lie to receiver 2 about what it received from the sender, right? So it cannot receive 42 and then claim to have received 43 because we require it to forward the signature. So that's what will come in and save the day. And in that case, we can actually solve Byzantine broadcast for all settings, also 298 corrupted servers out of 300. So digital signatures are much more powerful than having just authenticated channels. And then the last slide, because sometimes there's a little bit of confusion then about, but why didn't this scenario proof here? Why doesn't it also rule out to tolerate 1 out of 3 when we use signatures? Because the proof seems pretty robust, right? So let's just spend 1 minute on that. So notice that when I take party 1 here, in a case where we use signatures, then party 1 will use the secret key of party 1. It will have SK1, let's call it that, in its head. Because in the protocol, it will need to make signatures. So it will need that signing key to compute the signatures it would like to send to P2. So in that case, when I make kind of 2 copies of P1, both of them will use the secret key. And of course, it has to be the correct secret key, namely the one corresponding to the verification key that P2 and P3 know from some PKI. Then this figure here still makes sense. We can look at this thing here as a corrupted P1. P1 just made 2 copies of itself, fed them the correct secret key, and then ran both of them, one with input 0, one with input 1. But this figure down here now doesn't correspond to a corrupted P2 anymore. Because here's an honest P1 running with the secret key of party 1. Here's an honest P3. And then to run this stuff up here, you also need the secret key of party 1. And this, a corrupted P2 in this figure up here would not have, because each of these parties have their own secret key. Only P1 has SK1, only P3 has SK3, only P2 has SK2. So we cannot just pretend that this is a corrupted P2, because P2 up here, when corrupted, does not have SK1. Huh? So that's where the proof, the impossibility breaks, and that's how we sneak through the impossibility result. Okay, that's a lot of talking for setting this scene, but I hope this gives you definitely an idea what Byzantine broadcast is. Seeing, that there are ways to cheat, so it's a hard problem. And in fact, that we need to use somehow signatures to prevent some of these basic cheating strategies.